Today we are going to solve some of the previous CSIR questions. So this is the first question. The correct order of heat of hydrogenation for following compounds. They have given 4 compounds, so we need to identify which is the correct option. So before going to answer this question, first we need to know about the heat of hydrogenation. So just there are few points for heat of hydrogenation. So what is the heat of hydrogenation? So when we have a alkene, so to this we will add H2, so we'll get a alkane, and now some energy will release. That energy is called as heat of hydrogenation. So this reaction always exothermic, so because of that reason we'll get always the energy in the negative values. Okay, so now we'll see some of the points. So these points will be helpful to us to identify which is the correct option. The first point is stable alkenes having less heat of hydrogenation than unstable alkene. So we can say this one as like less substituted alkene. Sorry. So more substituted alkene is more stable, and this will be less substituted alkene. Okay, this is the first point. The second point is trans olefins. So among trans and cis, trans is more stable. So trans olefin is having less heat of hydrogenation compared to cis olefin. Third point, if number of double bonds are more, that will have more heat of hydrogenation. And we can also see we have 3 systems. This is called conjugated system, and this is called cumulated system, and this is called isolated system. Okay, so among these 3, which is more stable? Among these 3, no doubt that conjugated is more stable. And least stable will be what? So cumulated will be least stable. Cumulated means adjacent double bond will be there, because of that there will be some repulsions, so this will be least stable. Okay, stability order is A is more stable, then C, then B. So now heat of hydrogenation order will be reverse. B will be having more heat of hydrogenation energy because of it's less stable, and next C will comes and A comes at last. So this is the heat of hydrogenation for conjugated, cumulated and isolated system. So these are the 4 points we need to remember. And now we'll go for the question. Here you have, see here the question asked. So this is the question. So here we have 4 compounds. So this is the 1, 2 and 3, and 4th compound is here. Okay, so as we see here double bond is having no substitution. So here 1 substitution, and here also we have substitution, and here 3 substitution we have. So as we know that, so here we need to take this point. Okay, so stable, this is the stable. This alkene is stable because it's more substituted, right? So now we will arrange the stability order. So 4th is more stable, and we have next here we have trans as well as cis. So which is more stable? Trans is more stable, right? So 2nd, then 3rd, at last 1st. So now we'll go for the heat of hydrogenation. It's exactly opposite. So first is having more heat of hydrogenation, then 3rd, then 2nd, at last 4th. So the answer will be 1st, 3rd, 2nd, 4th. This is the answer. Next. Next question. The decreasing order of the following compounds. So we have imidazole, we have this compound, and this is called guanine, and this is pyridine. So here which is we can identify easily, least basic will be pyridine, and imidazole is more basic than pyridine. Now we need to identify among these three which is more basic. So there are four DNA bases. We have, these are very important. We have adenine structure is this, NH, this is adenine. Next we have guanine, thymine, and last cytosine. So among these four, if we see among these four, the more basic will be adenine, because here we have NH2, there will be plus R effect from this NH2, so because of that this is more basic. And least basic will be this compound thymine, because there is two carbonyl groups are there. So if you see order, adenine is more basic, then guanine is more basic, and then cytosine, at last thymine. So these are more basic DNA bases. So here we have guanine. So here guanine will come first, because the number of nitrogen atoms are more. We can identify through basis of number of nitrogen atoms also. So guanine will be more basic, and after that this compound comes. And now we have imidazole and pyridine. So among imidazole and pyridine, imidazole will be more basic, and pyridine comes at last. So this is the correct order of basicity. And here we have the correct order of electrophilic aromatic substitution of the following compounds. So here we have, here by elimination method also we can identify this answer, because we have pyridine here. So what is happening in case of pyridine? The electron density, most of the electron density is located on the pyridine. Okay, so pyridine is like electrophilic substitution reactions are completely ruled out in case of pyridine. Instead of on the carbon, electrophile goes and attacks to the nitrogen. So electrophilic substitution order for pyridine will be very least, so that this comes at last, this will the at last. And here we have chlorobenzene and indole. So N-methylated indole. So in indole, first we will see about indole. So here two groups are there. We have pyrrole as well as benzene. So pyrrole is electron rich compared to benzene. This we know that. So because of its five atoms are there, 6 electrons are located on 5 atoms. Here six electrons are located on 6 atoms. So because of that reason, pyrrole is more electron rich. So electrophile goes on to the pyrrole and nucleophile goes on to the benzene. So this is the reactivity order. So when we have N-methylated, after methylation of this NH, this hydrogen, the basicity of this electron density of this pyrrole ring further increases. So because of that reason, the electrophilic aromatic substitution is very faster in case of one, and the second option will be third, chlorobenzene, and last will be pyridine. So this is the this is the correct answer. So D will be the correct answer for this question. So here we have this reaction. So in the first reaction we have MCPB in the presence of dichloromethane. So this is a epoxide formation takes place. We have alkene in the presence of MCPBA. In DCM we have a epoxide formation. Okay, and next we have CH3 C triple bond CMGBr. So here this is a nucleophilic center, so this will open this epoxide. So this follows SN2 mechanism always. In the presence of base, opening of epoxide follows SN2 mechanism. Okay, so now let's imagine this is opening to above the plane and this goes and attacks from the below the plane. So it's opening from above the plane means this O minus comes above the plane, and this will stays below the plane. And further in the next step we have aqueous NaHCO3. This is for workup process. So this O minus will get converted into OH here. This is OH, double bond C, triple bond C, CH3. So next we have, this is the product A. Next we have Lindlar catalyst. Lindlar catalyst means PB. Palladium, calcium carbonate plus PbOCO CH3 twice and quinoline. So this is the Lindlar catalyst. So Lindlar catalyst converts alkyne into cis olefin or Z olefin. So that means here we'll get C double bond CH3 H and H. And in the next step we have acetyl chloride in the presence of pyridine. So we know that OH in the presence of acetyl chloride gets converted into OAC. This is very simple reaction. So here this OH will get converted into OAC. OAC double bond C HHCH. So this is the product B. So this is very simple reaction. We have in the first step we have MCPB oxidation, and further opening of epoxide, it goes through the SN2 mechanism, and further we have NaHCO3. It's just for workup process, and Lindlar catalyst converts this alkyne into Z alkene, and further we have a conversion of OH into OAC. So in the next we have this reaction. So here we have BH3 with THF. So we know that it follows syn addition, and BH3 comes at less substituted carbon, and here hydrogen. Okay, so in the next step we have NaH and H2O2. So in the next step we have a conversion of BO2 into alcohol. The mechanism here involves is H2O2 we have in the presence of base will get O minus OH, and this goes and attacks to the further here to the boron, and further we have a hydrogen, this group everything will migrates to OH. Okay, next we have in the next step we have PCC in the presence of dichloromethane. So PCC is the oxidizing agent. It converts alcohols into carbonyl compound. So this is primary alcohol converts into aldehyde. So this is product A. So in the product B we have a PH3P plus CD3I. So it forms PH3P plus CD3I minus, and if we have n-butyl lithium also, so that n-butyl lithium abstract one of the deuterium atom here, so it forms with TIG reagent. So now this goes and reacts to this carbon, so we get O minus, this is CD2, and ppH3 plus, and here reaction goes deuterium O ppH3. So now removing of pH3PO, it leads to form deuterium. So this is the product here we'll get. This is product product. I hope everything is clear. This mechanism is a little I'm not sure, means not that sure about this mechanism, that's why I'm not explaining. So I will explain in the later videos. So I hope it's clear. Thank you.